So, in the previous series of lectures, we were examining the solution of the diffusion equation. Okay. Which in this case was of the form k del square plus q times delta of x is equal to 0 for a point source. Okay, so, you have a 3-dimensional coordinate system x, y and z, and if there is a point source at the origin and if there is an observation point x vector, okay, whose displacement vector is this, then we saw that the solution of this equation is t is equal to 1 q by 4 pi k times the distance between the source and the observation point. Okay. And the flux vector is q into the vector x by 4 pi k into the magnitude of x, the whole cubed. Okay. And if you had multiple sources, okay, if you had multiple sources at different locations, okay, let us say you had a source, okay, q1 at the location x1 vector, okay, then q2 at the location x2 vector and q3 at the location x3 vector, and you wanted to find out what is the temperature at the location x vector. Okay. It is going to be the sum of the temperatures due to each of these individual sources. Okay. So, T will be equal to sigma, okay, Q I by 4 pi k into the distance between the observation point and the source point. Okay. Okay. And the flux vector will be equal to the summation I is equal to 1 to 3 of q I into x minus x I. Okay. This is a vector and x. So, on the left side the flux is a vector, on the right side, okay, I should note here there is just 4 pi, okay, there is no k here. On the right side x minus x I is a vector and this is divided by 4 pi into the magnitude x minus x I, the whole cubed. Okay. So, those were the expressions that we had derived. Okay. And similarly, if you had a distributed source, okay, such that the temperature field was governed by the equation k del square T plus volumetric source of x is equal to 0. Note that QV has dimension of heat energy generated per unit volume per unit time. Okay. So, that this dimension of this equation is correct. Okay. So, if you have a distributed source of that kind, okay, the solution is just the continuum equivalent of the temperature field for a discrete source, that is T is equal to integral dV prime, okay, Q of the volumetric source of x prime by x minus x prime the whole cubed. Okay, that is the temperature field, which is just an analog of this one, going from the discrete variable to a continuous variable, continuous heating, and q vector is equal to integral dv prime. Okay. Note that the observation point is x. Okay. The observation point is x, t of x vector. Okay. That is the observation point. That is the location at which you are observing the temperature. Okay. And similarly, the heat flux is observed at the observation point. Okay. So 4 pi k here. So, these are the temperature fields in an infinite medium where there are no boundaries. Okay. In that case, you can always use linear superposition for multiple sources in order to find out the temperature field simultaneously due to all of those sources, or an integral, okay, in order to find out the temperature field for a continuous source distribution where QV is equal to the energy generated per unit volume per unit time. This is the kind of source that you would have in a reaction, for example. If it were exothermic, the energy generated would be defined per unit volume per unit time based upon the reaction rate per unit volume per unit time. Okay. So, this temperature field is often written as what is called a convolution integral. Okay. Integral dV prime. V prime is the volume of the source. Okay. G of x minus x prime times q v of x prime. Okay. G of x minus x prime times q v of x prime. Okay. So, let me just put that in here. Okay. I will put that in here. Where g of x minus x prime is equal to 1 by 4 pi k into x minus x prime. This is called the Green's function. Okay. In an infinite domain. Okay, this is called the Green's function in an unbounded system. Okay, what if you have boundaries where boundary conditions have to be satisfied? So, we were seeing that the last time where we considered a point source, okay, plus q, okay, located at a distance L from a solid conducting wall. Okay, solid conducting wall at a distance, perpendicular distance L from this conducting wall, and we wanted to find out what is the temperature field due to this point source and the conducting wall. A conducting wall is one in which the temperature is a constant, because if it is perfectly conducting, there is no flux parallel to the wall. That means there is no temperature gradient parallel to the wall. That means that the temperature is a constant parallel to the wall. If you consider the temperature far away as T infinity and the wall as perfectly conducting, the wall temperature is also T infinity. Okay. Now, if the wall is perfectly conducting, then there is no flux along the wall, because the temperature is a constant along the wall. Okay. in the direction parallel to the wall, the temperature is perfectly a constant. Okay. Therefore, there is no temperature variation parallel to the wall, and therefore, the variation in temperature is necessarily perpendicular to the wall. It is in the direction perpendicular to the wall. That means that the flux lines are perpendicular to the wall, because the flux lines are in the direction of the variation of temperature. Okay. The flux line goes along the gradient of the temperature, negative of the gradient in fact. Okay. So, the flux lines have to be perpendicular to the wall, okay, if it is perfectly conducting. That means that the flux lines that emerge, okay, or that emanate from the source, okay, have to be parallel to the wall at the wall itself. Okay. So, that is the requirement. Okay. Now, for a point source, right, the temperature was given by Q by 4 pi k into x minus x prime, okay, where x I will call this as x s, okay, the source location. Okay. Okay. That was the temperature field due to a point source. This temperature field obviously is not a constant along a plane. Okay. This temperature field decreases with distance from the surface and from the point source, and you can see on this horizontal surface the distance from the point source varies. Therefore, the temperature varies, and this temperature field due to an isolated point source in an infinite medium does not satisfy the boundary condition on this surface. So, how do we satisfy the boundary condition on this surface? So, I had explained that briefly in the last lecture. I have a heat source plus Q at the location x s, where x s is the location of the source. Okay. Now, if and this x s is located at distance L, okay, from the source. Okay. Now, if I place minus q, okay, at a location x I, okay, such that this distance is also equal to L. Okay. Okay. So, you have a source x s strength plus q located at the location x s, whose perpendicular distance from the surface is L. I remove the wall and I place a sink minus q at the location x I, which is on the other side of the wall at a distance L, okay, from the wall. Okay. Then if both the source and the sink have equal heat generated and absorbed per unit time, then all the heat that is emanating from the source will get absorbed by the sink, okay, and the flux lines will travel from the source to the sink. Okay. And for these flux lines that travel from the source to the sink, you can show that at the surface itself the heat flux parallel to the surface is equal to 0. Okay. Heat flux parallel to the surface is 0 implies that the temperature gradient parallel to the surface is 0, and therefore, the temperature necessarily has to vary only perpendicular to the surface, and the flux lines have to be perpendicular to the surface. Okay. So, let us see how to show that. At some point on this surface, okay, at some point on the surface, let us sum up the fluxes due to the source and the sink. Okay. The flux due to the source will be along the radial direction from the source. Okay. So, it will be in this direction. Okay. There is a flux that is going into the sink. Okay. There is a flux that is going into the sink. Okay. That is also in the radial direction, okay, but it is inwards. Okay. So, it will look something like this. And these two vectors have equal magnitude and equal angle from the horizontal plane. Okay. These two vectors have equal magnitude because the source strengths are same. The distance from the source and sink is equal at this mid plane. Okay. and you can see that the horizontal component of these two are exactly opposite to each other, and therefore they cancel out. Therefore, there is no horizontal component to the flux, and the flux is necessarily perpendicular to the surface. And if there is no horizontal component to the flux, then the temperature does not vary in the horizontal direction, and this satisfies the constant temperature condition at the surface. Okay. So, therefore, I can satisfy the boundary conditions by putting another sink at a location xi. So, and this combination of source and sink will satisfy this correct boundary conditions at the conducting surface. Okay. So, by adding this image, this image source, I can satisfy the boundary condition at the surface itself. Okay. Now, this method can easily be extended to a distributed source. Okay. So, if instead of a point source I had a distributed source, having some q of v x prime. Let me write it clearer for you. And I wanted the temperature at some location x, and the condition is that T is equal to T infinity at the surface and T infinity far from the source, the distributed source QV. You can easily see that you can satisfy the constant temperature boundary condition by adding, by removing the surface. And in addition to the source at this location, I can add a negative of the source. I have not drawn the two to be identical, but if these two are mirror images of each other, if these two are mirror images of each other, this will identically satisfy the boundary condition of the surface, because at some point on the surface, for every point on the source which has some particular value of the energy generated per unit volume per unit time, there is an there is an analogous point where there is an energy absorbed per unit volume per unit time, and therefore, these pairs of locations ensure that the boundary condition is satisfied for all locations on the source. So, for a distributed source you can just add an image distributed source in such a way that the boundary condition is satisfied. So, this is a simple extension of the method of images for a distributed source. So, the temperature will be T is equal to integral dV prime of qV of x prime by 4 pi k into x minus x prime magnitude, the magnitude of that, plus integral dV prime qV of x I prime. This should be a negative sign because this is in opposite in sign, divided by 4 pi k into x minus x I prime, the magnitude. So, this is a simple extension for the method of images for a distributed source. this was for a point source. Okay. I have just extended this for a distributed source. Okay. It is a straightforward extension. Okay. And you can also write this as integral dv prime of g of x minus x prime qv of x prime, okay, where this Green's function is equal to qv of x prime by 4 pi k into x minus x prime, okay, plus qv of the image, okay, divided by okay. So, this is the Green's function for a plane surface where xi and x prime are related. Okay. Xi prime and x prime are related by the z coordinate of xi prime is negative of the z coordinate of x prime. X and y coordinates are the same. Okay. So, this is an image source which is located at a distance below the surface. The distance below the surface is identical to that of the source above the surface for each point on the source. Okay. So, in this way I get back the same expression for the temperature field, except that this Green's function is slightly modified. Okay. This is called GD, that is, it is called the Dirichlet Green's function. Okay. This is the Green's function which ensures that the temperature is a constant on a surface. Okay. For a plane surface, it is relatively easy to identify what is the Green's function. If the surface were more complicated, it would be more difficult to identify. Okay. So, this kind of an image source or image sink ensures that the boundary condition that the temperature is a constant on the surface or the surface is perfectly conducting. Okay. What if I, on the other hand, had a perfectly insulating surface, okay, and I had a point source Q and at the location xs. Okay, it's the point source is Q, it is located at xs, okay, and the surface is insulating. Okay. That is, there is no heat flux through the surface. Okay, there is no heat flux through the surface. That means that the flux lines have to go parallel to the surface. Okay. Okay, that means that the flux lines have to go parallel to the surface. There is no component of the flux perpendicular to the surface because it is insulating, it is perfectly insulating. How do we satisfy these boundary conditions? Okay. As you might have guessed, it is quite easy. Okay. What I do is I have removed the wall, put in a source. Okay. Okay. At the same distance L from the surface. Okay, at the same distance L from the surface, and I put in a positive source. Okay. At the location xi, okay, also at a distance L from the surface, okay, on the same perpendicular line as the source. Okay. So, what happens if you do these two? Okay. The flux lines will actually go like this from symmetry. Okay. And at the surface itself, the flux perpendicular to the surface will be equal to 0, okay, due to these two flux lines. The component of the flux perpendicular to the surface will be 0, and it satisfies the condition that there is no heat transfer through the surface for an insulating surface. This once again is quite easy to see. Okay. So, let us say you are at an observation point here. Let us say you are an observation point here. Okay, the heat flux due to the source is going to be along the line joining the source and the observation point. Okay. The heat flux from the image source is going to be along the line joining the image source and the observation point. And as you can see, the magnitudes of these two are equal, and the components along parallel to the surface are equal. The components perpendicular to the surface are opposite of each other, because at this plane the distance from the source and the image source are identically the same. Okay. And therefore, you get no component that is perpendicular. Okay. The net flux is going to be along the surface, okay, in this case. Okay. So, putting an image source which has the same sign as the source results in a 0 flux boundary condition for an insulating surface, and the temperature field due to this is equal to Q by 4 pi K to with a plus sign. Okay, so, that is the temperature field. Okay, this ensures that the flux perpendicular to the surface is identically 0 at the surface itself. Okay. And for a distributed source, I can get T of x. Similarly, for an insulating surface as integral dV, okay, Q of x prime by 4 pi k into x minus x prime plus QV, okay, of x I prime by 4 pi k into x minus x prime. So, this is the temperature field for a source or a distributed source or a point source near a wall where you have to satisfy the 0 flux condition perpendicular to the wall, okay, if it is perfectly insulating. Okay. Okay, so, from this you can get the Green's function expression for this as well. Okay. So, the Green's functions g of x minus x prime is equal to 1 by 4 pi k into x minus x prime plus 1 by 4 pi k into x minus x I prime. Okay. And the temperature can be written as integral, there is a prime here, my apologies. Where Gn is called the Neumann-Green function, which satisfies the 0 flux boundary condition across the surface. Okay. So, for a horizontal surface this is quite easy to do. Okay. For a horizontal surface this is quite easy to do, and this can also be done when you have, let us say, two surfaces next to a corner and so on. Okay. So, there are many situations in which this can be done. This is not yet a systematic procedure. Okay. This is not yet a systematic procedure for getting the Green's function. Okay. So, the next lecture I will briefly discuss a systematic procedure for solving the temperature equation in order to get the Green's function for a distributed source in a domain where there are boundaries, where boundary conditions have to be satisfied on the boundaries. Okay. So, how do we do that in that case? I will continue that in the next lecture. I will see you then.